start with just a statement of the result. So numerical quintic n-fold is of a variety x. Obviously I want dimension x is n. I'm going to have not too singular. Let me come back to this. And then I want that kx is 3 minus n times a. And so here a is an ample Cartier divisor. Yes, and I want this a to the power of n is 5, and h naught of a is n plus 2. Right, so let me start off here by saying you could insist on non-singular, or you could insist on at worst ordinary double points in codimension greater than or equal to 3, or you could allow here terminal canonical singularities. So you might start off by saying this is the natural condition, and then when you try to construct examples you might be obliged to put singularities. So I think everybody here knows the case of x, a non-singular surface of general type. So then n is 2, and then we're saying kx is an ample Cartier divisor, and a squared is 5, and h naught of a is 4. So this is the thing that Horikawa called a numerical quintic. So around 1980, Horikawa proved that there are two cases. So either a is free, the result in dimension 3 and more, I think Horikawa told me around in 1980. And I think it's not published. I don't know. It may be in one of these Japanese, conference proceedings and so on. So either a is free, and then x is embedded by a into p n plus 1 as a quintic hypersurface. So or a has a single transverse space point and then if you do the map given by x, it blows up this point and it goes to quadric in p n plus 1. So then this x twiddles, and this x twiddles is the blow up of a single non-singular point. And then this map here is a 2-to-1 cover, a generically 2-to-1 morphism, and the Q is a quadric of rank 3 or 4. So I think probably most of you know the proof of this statement in the case of a surface, and basically it's the same proof. You just have to you worry a bit about how you resolve the base locus and how you use the condition that a to the n is 5. And so you use it you think of the a to the n as being multilinear, as being a linear operation several times, and each time you take away a piece of the base component, you're only allowed to lose at most 1. Okay, so I hope the thing that's happening is clear. When this a to the n is 5. 5 is a small number. So the only thing that can happen here is that I lose 1 from the degree of the map, and then afterwards I have a 2-to-1 map to a quadric. So the 5 is 1 plus 2 times 2. Degree of the map times degree of the image. And that's the only possibility. Yes, and so there's this picture that looks like this. Type 1, type 2, A, and type 2, B. Right, and so...
The only thing which is not clear is why the rank
is 2B.
why the rank can be higher.
So if you want a simple geometric explanation, I've blown up that point. And so there's an exceptional plane there, and it's got to get mapped linearly. Okay. So it's mapping into a quadric that contains a very big linear subspace. So, there will be sort of... this is not, in itself, this result doesn't guarantee that these components actually exist. Right, and so this is the thing that I'm going to tell you about. So type 1A, sorry. So my contribution to this, in terms of the result, is that 2A exists, and V has generically, maybe I should say X instead of V, generically ordinary double points in codimension 4, and in type 2B X has in general, generically, ordinary double points in codimension 3. So if we were talking about Calabi-Yau threefolds and we were insisting on non-singular, then that's what you see. Right, and so So these guys have class group of X is Z plus Z, corresponding to the two rulings of quadric of rank 4. And this one has class group. So if we were lucky and we managed to find a non-singular guy there and a non-singular guy there, and for example if we're a threefold, it's guaranteed that these guys can't be topologically equivalent, right? Because this one has second Betti number equal 2 and this one has second Betti number equal 1. Okay, so I'm going to explain to you how you can really construct these and how you can construct the degenerations between them. So I'm going to give you an algebraic construction here of threefolds called, this is family I'm not quite sure which is A and which is B. Anyway, there's going to be another family here. I think this is family B and this is family A. I'm sorry, I can't remember my own notes. Yeah. And so these are going to give me nice varieties. So A has a parameter lambda, and this is really two different families. A with lambda not equals 0, and A with lambda equals 0. And this is B with x2 equals x2 primed, and B with x2 equals x2 primed. Right, and this part here is type 1, that's this family, that's the one that's the ordinary quintics. Then A with lambda equals 0 is this case, and that's the same as B with x2 equals x2 primed, and then B can go off like that where the quadric's allowed to have rank greater than 2. So what I'm really talking about is Gorenstein codimension 4. I'm not going to go into a lot of details about this. So I've been involved in writing 3 or 4 papers on this topic in the last couple of years. If you Google Reid and Gorenstein codimension 4, or if you go to my website plus 3 folds, you'll find 3 or 4 papers on this topic. So I have lots of experience of writing down these Gorenstein rings in codimension 4, and everything I'm saying about these families is so the thing that I really want is to find, this is the aim, to find these varieties as regular pullbacks from a key variety, or from key varieties. Right, so let me, before I get into any details, let me explain what this regular pullback is, something that everybody ought to know. So, if I've got W in an ambient space, AN, right? And so I'm going to give this meta definition of what is a key variety. Right? This is not a mathematical definition. A key variety is any affine variety that I want to use as a key variety. Yeah, and so this is a psychological state. I take this variety and I want to think of him as a key variety, right? And what does it mean? It means that I want to do a regular pullback. So what I'm going to have is a morphism from some ambient ring, some ambient scheme. So think the R stands for regular scheme or regular local scheme here. So I'm trying to map this guy into there by a morphism phi, and I want to take the pullback here. So I want X in there to be the pullback. Right, and so a regular pullback.
You might give as example a determinant of variety. Could be a key variety.
So let me give an example. Let me take the origin in A1. Right, perfect example of a key variety. So every hypersurface is a pullback from this. So I take, what it means is I'm going to take spec R, I'm going to take a morphism to there, which is just the same thing as an element F in R, and then I'm going to take F to the -1 of 0. Yeah? And I insist that this is regular, which means that I want this guy F here to be a non-zero divisor in a non-singular ring, in a regular ring. F is a non-zero divisor. Right, or I could take 0 in an defined by x1 equals x2 equals xn equals 0, and then this is a model for all codimension n complete intersections. Right. So the thing that Fabrizio was getting at was, for example, if I take the affine Grassmannian 2,5, right? So this is contained in the Plicker space, so A10, which is wedge 2 of C5. Right. So this guy here is the variety defined by Pfaffians of skew 5 by 5 matrix. So I take the matrix, which everybody knows from writing down, so matrix with M1, 2, M1, 5 down to M4, 5. Right, and so these are the Plicker coordinates. These are just coordinates in this space, and then I command that all the 4 by 4 Pfaffians of this matrix are 0. That defines a variety like this. Right, and so this regular pullback here is going to be a morphism from my non-singular ambient ring there into this AN, phi, and then here I'm going to have X. And so what this means is phi means substitute Mij equals a polynomial, sorry, phi upper star Mij in R. So choose some elements in there and then take exactly the same equations I had here and allow them to generate an ideal in X. It's just the ideal generated by those maximal Pfaffians, but with this thing. Yeah, and so the key variety was used, I think, classically in the theory of determinantal varieties. Right, I haven't told you what regular means here. So what I mean by regular pullback is that I want to take X to be the intersection of the graph of phi intersect this spec R cross AN. Yes, and so the graph of phi, the graph of a map, is a complete intersection. It's just given by xi equals phi I. This is a complete intersection there. Right, so inside here, I'm sorry, intersect x cross a w cross an. Right, and so the condition is just that xi equals fi is a regular sequence in 4w cross spec R. Yes? So this condition here, asking for these guys to be a regular sequence, this is particularly easy if this ring is Kern-Macaulay. If we know that W is Kern-Macaulay, which we certainly know there, then the condition here is just that when I cut down to the right codimension. It just means that by making this substitution, I keep the codimension the same. So I want to tell you how to start on this problem, and basically the key the main observation is to understand the curve section. So this was, of course, already in Horikawa, and it was the subject of a thesis of Harvard student Ed Griffin in 1985. And so Horikawa says, suppose that we're in case 2. So P is in X is a base point. So let's think of X as being a surface for the moment, right? Then it means that I take these A, this is Kx, and it's got so I take a curve in there. So I said a single transverse base point. That means that there's a point of the surface here, and the curves in it pass through it like this, where they're generically non-singular and meet each other transversely. Right? By Bertini's theorem, I can assume the curve is also non-singular outside there. Right? And so the thing already Horikawa said perfectly simply about this curve is that C is hyperelliptic of genus 6, and Kx restricted to C is P plus twice G12. Right? And so this is almost obvious. The curve C is a non-singular curve. If I do this Kx restricted to C, I get something which is in its half-canonical system. I'm assuming it's got a fixed point, right? So it is a fixed. So this thing here is a G25, right? And it's got a base point. So it's so actually it's a P plus a G24. And Clifford's theorem says the only way I can have a G24 is by having a hyperelliptic curve and then taking twice the canonical system. And moreover, because I said that twice of this divisor here is the canonical class of C, it follows that 2P is in the G12. So P is a Weierstrass point. Yeah? And so my method of working, I sort of pretended I'm doing geometry here, but really my method of working is very, very algebraic. So I want to understand the graded ring of X and A, and the first thing I'm going to do is the graded ring of X and of C and A restricted to C. Right, and so this is just a graded ring of C and 5P, where P in C is a Weierstrass point. On a hyperelliptic curve. Yeah? And so, this ring, by now I have lots and lots of experience working with this, so this is an easy calculation. And so the right way to think about this is this. Suppose I take R, C, and of P. It's a universal, it's a common experience here that if you can replace the ring by a bigger ring, it's always easier to calculate it. Right? And so this ring here is of the form ground field. The ground field, I can take the ground field to be C if I want. Lovers of characteristic P can make their own deductions. U, V, W, where this has got degree 1, degree 2, degree 13, divided by a single equation which is F26 of U, V, W equals 0, or in other words, it's the equation W squared equals u times f12. Sorry, something like this. Have I got this right? This is, genus of C is 6. So it has 2g plus 2 branch points.
U squared V is hyperelliptic series, right?
And so it's, so I'm supposed to be writing down, so I've got a point P here, which is the point at infinity, and then I've got 13 other points.
Okay.
So I'm getting w squared equals f26 of u and v, which is f13 of u squared and v. This is P1. He's got coordinates T1, T2, and I'm identifying T1 with u squared and T2 with v. This is a graded ring construction. Yes? So this is on my graduate student worksheet on my web page. So you're supposed to know this. Yeah? And so, look, everybody knows the equation of a hyperelliptic curve is y squared equals f14 of t1, t2. Right? But I've taken one of these points and sent him off to infinity. Yeah? So I'm separating the Weierstrass points into 1 and 13 others. And I get this is this. Right, so a hyperelliptic curve here is C is a curve of degree 26 in weighted projective space 1, 2, 13. Okay, so I'm not interested, I won't be able to extend this ring to the surface. However, so the ring that extends the surface is C and 5p. And so what I'm supposed to do is taking this ring CP and truncate in degree 5. So I write down only the elements in that ring whose degree is divisible by 5. Right, and I'm going to take degree 5 in these variables and then I'm going to divide by 5. So when I do this, this ring here is going to have elements u to the 5th, u cubed v, uv squared in degree 1. So it means degree 5 in this ring, but when I do this truncation, I'm going to divide by 5, right? And then what am I going to see in degree 10 in these? I'm going to see things like u to the 10th and u to the 8th v. So I'm seeing all the quadratic polynomials here. And then at the end of this, I'm going to see v to the 5. Right, v to the 5 is of degree divisible by 5, it's of degree 10, so I'm writing him down as degree 2 here, and everything else here has got u's in it, has got at least 2 u's in it, and so therefore it's a multiple of, it's a polynomial in those. Yeah? And then in degree 3, I'm going to see u squared times w and v times w. Is this okay? So I'm calling these x1, x2, x3. I'm calling this one here y, and I'm calling these ones z1, z2. Yeah? So this is a standard calculation. I've done this calculation many, many times. So look, what's going on here is that there's a ring here that we understand perfectly well, and then I'm taking a sub-ring of it. It's a ring of invariance of a group action of order 5 if you want, or it's just this truncation. So the point is I have these elements u to the 5th, u cubed v and so on, but it's forbidden to use u and v as names, right? And so I'm only allowed to write down x1, x2, x3. There's a kind of, forbid. So I told you the generators of the ring. Right, and I have to tell you the relations that hold between the generators. Right, and so everything, the guys I wrote down are monomials in things that we already understand perfectly well. And so the relations in are C5P. Well, let me do this quickly. I'm going to write down x1, x2, x2, x3, x3 squared, y, z1, z2. And I'm going to write wedge 2 of this equals 0. Right, so what this means is x1, x3 equals x2 squared, and x1y equals x2, x3 squared, and etc. Yeah, so there are six relations. Yeah, and so if you write out the 6 relations, it's sort of quite complicated. But the thing it's telling you is that the ratio here, the common ratio, is u squared over v, right? And so I'm doing an elimination. U squared and v are not elements of this ring, so I'm not allowed to write them down as relations in the ring. However, the relations that are there are just to do with this. Yes? And so that's 6 of these relations, and you'll notice that what I've done here is really to do with the orbifold curve P1 marked with a half point P. Right, so T1, if I think of T1 and T2 on P1 as coordinates, then I really sort of, T1 vanishes at P, and I have a square root of T1 in the orbifold ring. Right, but I haven't used in any way the equations I haven't used the equation W squared equals F13. Right, and so then there are 3 more relations. 2 more relations involving Z1. So 3 more relations. Let me write what the relations are, saying Z1 squared, Z1 Z2, Z2 squared equals So I'm going to write down that F13. So F13 is this equation in u squared and v, right? And then I'm going to multiply him by u to the 4th, or u squared v, or v squared. Yes, and so this is the place I've got to write down the equations involving Z1 squared and Z2, and the thing I'd really like to do is just take W and write W squared equals F13. That's one equation, right? However, the W and the expression F13 are not invariants, are not in the ring, and so I have to sort of compromise a little bit and write down multiples of those equations. So when I write down Z1 squared, I'm taking the F13 here, multiplying him by u to the 4th, and then this square brackets means...
I'm a bit confused. I mean, wedge 2 subdivided into dimension 2.
This is codimension 3 in Z1, Z2. It's like the equations of P1 cross P3. This is the equations of a scroll, right? This is six.
Okay, so your border is with 3. Okay, sure.
So, you know, this is not completely general matrix. If this was y1 and y2, which it will be later, then this was x2 and x2 primed, then the thing I'm just writing down is the equations of P1 cross P3 in Segre. Right? And so the square brackets here means I take these expressions here, which are of degree 30, in U and V, into quintics, into sextics or whatever they are, in x1, x2, x3, y. Right, and this rendering process is not trivial and is subject to one tiny little subtlety. Right, so sorry, maybe I'm taking a little bit too much time over this. So I've got this guy F13. So, you know, this F13 came from T1, T2, and so he's the sum of terms like T1 to the 13th and T1 to the 12th, T2, and so on. T1 to the ith, Tj to the 13 minus I, and so on. So every term here has exponent I greater than or equal to 3 or j greater than or equal to 8. Right, and some of them have both with a bit to spare. Right, so I can take this expression here and write him in the form A10 T1 cubed and then minus B5 T2 to the 8th. Right, so take all the terms I want divisible by T1 cubed and just shove them here. Right, and now render this in x1 up to y. Right, and then all the remaining terms, the ones that are not divisible by T1 to the 3, are then divisible by T2 to a power bigger than 8. Right, and so I just put all of that together like this. Yes. So when I do this T1 squared F13, T1 T2 F13, and T2 squared F13, right, then I have two choices. I can render them as, so I'm giving up. I'm going to put on my glasses too. Right, I can render this as A x1, A x2, A x3 minus B x3 to the 4th minus B x3 squared y2 minus B y2 squared, or as B alpha x1 squared alpha x1 x2 alpha x3 2 squared and then minus B x3 to the 4th minus B x3 squared y2. Yeah, I'm just taking this expression, so if I take this and I multiply them by t1 squared, I'm seeing x1 to the fifth times a, right? And so I can write that as, t1 to the fifth times a. And so I can write this in terms of these x1, x2, and so on, right? So if I was doing this, I could say, well, here I'm taking alpha x1 and translating to a, right? And then this thing here is really, x2 squared is x1, x3, and so I could just translate from there to there, right? Now, so this is really the key point of the whole calculation. This is the thing that separates the two components of that Horikawa moduli space, is this choice. So when I'm in this ring here, the ring of invariance, when I'm in this ring here, the equation I've written down there, x2 squared, x1, x3, is an identity, right? x2 is that, x3 is that, x1, x2, x3, and the expression that's written there is an identity. However, when I'm in this ring, in this ring here with these generators, it's a relation. And after I've deformed, even after only just one infinitesimal deformation step, it's an equation modulo the deformation parameters, right? So here you choose A or you choose B, and you start deforming according to what you can see, and you get different answers. This is a subtle point, and everything I'm going to say from now on depends on this choice. So B. Let me look at this B. So what have I got here? x1 squared, x1, x2, x2 squared, and here it's x3 to the fourth, x3 squared, y2, b, y2. This is called rolling factors. Right, I write down z1 squared equals alpha x1 squared, z1 z2 equals alpha x1 x2, z2 squared equals alpha x2 squared, and then minus b x3 to the fourth minus b x3 squared y, and then minus b y squared, right? And I have the monomial equations there, and going from there to there, the two steps there replace an entry of the top matrix, of the top row of the matrix by the second row. Right, so that variety up there defines something which is in codimension 3 in Cohen-Macaulay, and here I'm defining a divisor in there. This is a Weil divisor contained in that codimension 3 thing. So so the fact that there are three equations here, so in the normal event I divide by 3 equations, I cut the codimension by more than one. I cut the dimension by more than one. However, these 3 equations are really just one equation rolled over, one equation turned over in a linear system. Right? And so this expression here is explicitly quadratic in the rows of the matrix. Right, and this means I can just take my matrix there and replace them by x1, x2, x2 primed, x3, y1, y2, z1, z2, and then adapt these equations. Adapt these equations.
So now before you had just one y, now you have y1 and y2.
So I'm just replacing. I'm replacing the entries in the matrix by generic entries.
Okay.
Right. And so I can specialize this by putting x2 primed equals x2 and y1 equals x3 squared and y2 equals y. Right? But this is so these are nine equations define the codimension 4 Gorenstein subvariety scheme in an ambient space with all those guys as parameters, right? And the point is here that because I have this expression here explicitly quadratic, I'm allowed to replace this x2 in this matrix by x2 primed. Right, I can replace the matrix by generic entries. And by doing this, this allows the quadratic of rank 3 to grow up into a quadratic of rank 4. Yeah? And so here on the other hand, I'm also doing one of these rolling factor things. Right? I'm replacing, when I replace x1 by x2, I'm replacing something in the top row of the matrix by something in the bottom row of the matrix. Then when I do this, x2 goes to x3, I'm also replacing something in the top row of the matrix by something in the bottom row. However, this thing here depends on the coincidence x2 equals x2 in the matrix. So when I do this, the matrix cannot change from being rank 3 to rank 2 compatibly with the syzygies, all the syzygies. I'm sorry? So in this matrix here is not generic, right? In particular, it has entry x2 there and entry x2 equal. Yeah, yes. So it depends on, I'm not allowed to put in a new variable x2 primed in my matrix. I've got to keep the old symmetric guy. So on the other hand, now I do get a different freedom, right? In particular, I get the freedom for this hyperelliptic thing to jump up and be a non-hyperelliptic thing, so to jump out of his plane. So at case B, basically nothing interesting is happening here. I'm working inside this thing, which is like a scroll, and my things are going to be either divisors in a scroll or they're regular pullbacks of divisors in the scroll, right? So the quadratic can go to a quadratic of rank 4, but they will still be hyperelliptic. I'll still have this z1 squared, z1, z2. There's no way of making the equations become non-hyperelliptic. So on the other hand, case A, I can rewrite the equations. In the form as Pfaffians of, so I'm going to write down a 6 by 6 extrasymmetric matrix. So let me write them down first and comment what it is that makes him extrasymmetric, what good he is to me. In this form, I'm going to write down 0, x3 squared, y, x1, x2, x2, using this symmetry, x3, then z1, z2, z1, z2. Then I'm going to write A here. Then I'm writing 0, b, x3 squared, b, y2. And to be sort of suggestive, I can write 0 times b here as well. The thing I'm writing down there is a skew, antisymmetric 6 by 6 matrix. So this is the guy, this is M12, this is M16, and I'm sparing myself the trouble of writing down zeros down the diagonal. Right, this guy's M56. Right, and so his 4 by 4 Pfaffians are exactly the 9 equations of RC5P. Right, namely, so when you calculate Pfaffians, the rule for Pfaffians is I'm going to write down Mij MKL minus Mik MJL plus MIL MJK. So these are Plicker equations. The Plicker equations are Grassmannian, or you can think of them in lots of different ways. But anyway, what I'm going to do is that times that minus that times that plus that times that. Yeah, and so the fact there's a 0 there means I get 0 times Z1 equals, well, you know, the 2 by 2 minus of this, the 2 by 2 minus of this thing at the top. Yeah, so when I do the Pfaffians, him times him, or him times him, or him times him, I'm getting 0 times those entries, and then I'm getting the 2 by 2 minus above. Right, and so the first 6 equations there are just particular Pfaffians of this equation. Right, now I'm going to write down Z1 squared equals x1 times a minus something here. Right, and so Z1 squared is the Pfaffian. So the Pfaffian, this entry here is the entry 3, 4 of the matrix, and then I'm going to times Pfaffian times 1, 6. So it's 1, 3, 4, 6. So I'm supposed to do 1, 3 times 4, 6. So this is saying Z1 squared equals a x1 minus b x3 squared to the 4th. Right, etc. Yeah? And so I have this clever trick here. I'm not explaining where the clever trick comes from. If you want to know that, you have to read Tom and Jerry. Right? But this set of 9 equations comes naturally as the Pfaffians of this extrasymmetric matrix. So what's extrasymmetric about him? Well, he's a 6 by 6 matrix, but he's really 3 by 3 blocks. Yes, and this block here is symmetric, right? So this x2 equals x2 is part of that, you know, this coincidence. I must maintain this coincidence x2 equals x2 to have this symmetry. And then the z1, z2a is that's just my way of writing it in, right? And then this block here is equal to this block here. Rather, there's a little factor here, a little polynomial factor b times this block. Right, and so I'm not telling you more generally what extrasymmetric is. However, when I have an extrasymmetric matrix, he's a 6 by 6 matrix. So above the diagonal there, you see 15 elements. 15 elements, but there were 6 coincidences. There are 3 coincidences involved in saying this guy's symmetric, and there are 3 coincidences involved there. So instead of having 15 independent entries, there are 9 independent entries and 6 repeats. When you calculate the Pfaffians, you find also 9 independent Pfaffians, the ones I've written down, and 6 repeats, just from the symmetry of the matrix. Right? Anyway, the upshot of this is going to be that I can put lambda there. Right? And so I don't have so much time. So the key variety that I'm really interested in, or in this particular graded manifestation, the key variety I'm interested in is this. So write down m sub lambda, and this guy here is lambda, y1, y2, x1, x2, x2, x3, z1, z2, z1, z2a, and then here I'm going to write down lambda times b and by1, by2. Right, so the same, I've preserved the extra symmetry, right? I've replaced the y1 and y2 by independent variables instead of having x3 squared. Yeah. Sorry, that should have been a y. That should just have been y. Yes. And so let me now define CV. This is my key variety. So he's contained in A9 with coordinates, I can't read, it's going into x1 up to x1 up to x3, y1, y2, b, a, b, z1, z2, right, times a1 lambda. Yeah, and so I'm just saying all of the guys in there, all of the guys allowed to remain in the equations are independent indeterminates. So just consider this equation here. Just to consider this variety. I say, if I take CV and I evaluate to the point where lambda is not 0, then this here is A5, right, with coordinates x1, x2, x3. I think y2's gone or something. I mean, one of the y's has gone. Y1, y2. Right, because, so now instead of having these 2 by 2 minus equals 0, now I have lambda times z1 equals these 2 by 2 minus. That means I can eliminate z1 and z2. They're not independent parameters. They're part of the, they're already contained in the polynomial, right? And so it's the graph of functions a, z1, z2, b over a5. Right, and so this is just the graph of a function. So write down what z1 is according to this rule. z1, z2, a, b, also b you have to divide by lambda squared, but still you get b. And then you can check easily, or I can check easily, you can check that the remaining Pfaffian equations are satisfied identically. Right? And so this is just a completely trivial thing. I'm writing down A5. I'm writing down equations that define A5 and that are the graph of functions over it. Right? And so when lambda equals 0, I get this CV, and he's codimension 4 in A9 with all of those parameters, and he's codimension 4 Barenstein. Yes. So I started off with this curve C, and the ring of C, and the canonical class of the surface A restricted to C. Right, and when lambda, so here, in addition to the equations defining the key variety, I still have x1, x2, x3. I put y1 equals x3 squared, and I put a equals a quintic in in x1, x2, x3. right? And so then C lambda, so don't change anything else in the equation, just put back the original equations I had and write down C lambda, and you'll find that C lambda is isomorphic to C5 in P2, right? And so this is the way, you know, a hyperelliptic curve, which is sort of lying flat over a conic in P2, is suddenly allowed to spring up into life, you know, like Lazarus rising from the dead. Yes? So all I can do this C lambda, I can think of as being proj of
Y2 is 0.
Y2 is whatever this is. Y2 is in B. I'm sorry. B equals Y2 plus a bit. So if I'm just concerning the original C, then I don't have all of these extra things. I don't have B and A as independent variables, right? But yeah. And so all of this was, I can do all of this inside this ambient space. So for this I don't need regular pullbacks, I just need to write down these equations inside the ambient space. And I get some ring there. When I take proj of the ring, I get C5 in P2. Right? But for the, if you want to do, for example, a Horikawa surface, or the threefold that I'm more interested in, then, you know, there are only 3 variables here of degree 1, and so I can't possibly do the surface. So the statement is that that now so I'm going to take, at this point it would be convenient to have a completely different set of letters, but I'm just going to use the same. So I'm going to take R is polynomial ring in variables x1 up to xn, and then y1, y2 only, z1, z2, and he's graded polynomial ring with degree 1, 2, 3. Right, and so I set B equals.
There is x1, xn. There is an x missing.
You're right, it's xn plus 2.
Okay, but these are all x, n plus 2 x's.
There are n plus 2 x's, yeah, and I'm sorry, they're not the same as the x's before. I'm going to substitute new x's for old x's, right? And so B is B2, y1 is y, and A is A5. So I want this to be 1, 2, right? And so this is a general form of degree 2 in x1 up to xn and y. Right, so this is a general form of degree 2, and this is degree 5. Right, then so these substitutions here is just replacing the entries in this matrix with anything I like here. Right, in other words, replace the entries in M lambda general elements.
I'm confused. So y2 in the matrix is y2 coordinates.
I'm going to substitute this for y1.
That's y1. Okay.
Right. And so, sometimes I need the y2. Right. Okay. And so then, when lambda is equals 0, I get type 2b. I get an n-dimensional. I get a quintic. I get a numerical quintic x, with this property that x has a canonical model, a quadric of rank 3 in P n plus 1. Right, this is just the map defined by x1 up to xn plus 2. Yeah, he's a double covering, and the equation of the double covering is you have to figure out what z1 squared, z1 z2 z2 squared are from the matrix. Right, when lambda is not equal 0, you get a x is isomorphic to a quintic, a general quintic in P n plus 1. And the general just becomes, so the fact I get a quintic is because I can eliminate y1, y2 as a function of the xi's. I can eliminate also y2 as a function of the xi's, and I can eliminate z1, z2 using this matrix. Right? So that's not the hard point. The tricky point is non-singularity. Yes.
No, if you need 5 minutes.
No. The tricky point is the non-singularity. And so this is sort of basically, if you want to, you can do computer algebra. Then in type the thing I said in type 2a, x has is singular, has ordinary nodes in codimension 4. So the nodes are happening over, I've got this Q here, and I get a quadric in the vertex of the cone. Yeah, and then in the case 2b, x has ordinary nodes in codimension 3. Right, and so everybody knows that when you make some construction of algebraic surfaces or algebraic varieties, you have an idea for making it. At the end of it, you have to do a horrible non-singularity calculation. So this is sort of typical thing here. And I don't really know how to do this in a very clean way, but by doing, in computer algebra, it's perfectly clear. Right? And so, there is the type 2b. If I think you can give sort of classical double covering constructions here, and you will find that you have singularities at so in particular in the Calabi-Yau case, where these are threefolds, this x, the 2a guy, is non-singular and has canonical image a quadric of rank 4, and the 2b guy has 2 nodes, right? And so there's an orbifold orbifold transition, a conifold transition happening at these 2 ordinary nodes of x, right? And then the variety can smooth out in a completely different direction to a non-singular quintic, right? So this is very, very unexpected. I mean, when we do Fano threefolds, Q Fano threefolds, we have this 300 families of 300 or more constructions of Fano threefolds, and they always come in 2 families. There's always Tom and Jerry, and they're always in the same component of the Hilbert scheme, but topologically different, varieties with different Betti numbers. So here, I don't think I was expecting to see that the Horikawa quintics and the Horikawa, these things that map to 2-to-1 to quadrics are actually topologically different, but they obviously are. Okay, I'm sorry I went over time. So I have to thank, on behalf of the absent organisers, I have the pleasant task of thanking the participants for coming and listening so patiently.